going to be Marco Romito from the University of Florence, and he's going to talk about the analysis of a model for amorphous surface growth.
Thank you. Okay, I'd like to thank the organizer for the invitation, and more generally to the invitation to the whole period that I'm going to spend here, which is a beautiful environment, and I'm really appreciating it. Okay, I'm going to present a work which has been developed partly with Franco Frandoli and essentially with Dirk Blumker, which is sitting there, so you know him. And okay. The first part, I'm going to give a short introduction on the model and what is the physical meaning, interpretation, why it might be interesting, and all the physical interpretation will stop in the introduction. So from the second point on, we will get math. Okay, the first issue we are going to discuss is the existence and uniqueness of stationary state for the stochastically forced equation, and which is quite odd because, as we will see, we do not know if this problem has a unique solution or not. And we will do all this by using a technique that we have been developing with Franco in a different context. And this presumably will take most of the time, say 60%. And then in the rest, I will discuss about some issues on how to understand the problem. And so the third and fourth part will be essentially on the deterministic problem and on how this can relate with the understanding of the stochastic equation. The last part is just a discussion on the two-dimensional case, which is the physically most interesting, although is for the point of view of the analysis, is also the most difficult. Okay, so let's start with the model. Here is the equation. It can be in one dimension or two dimension, but for the first part of the talk, I will discuss about the one-dimensional case. Okay, so the idea of the model is that, you got from the title, is an equation which models the growth of surfaces. There is some kind of mass falling falling down. And yeah, exactly. And we have a few different terms that which take into account different part of the phenomenon. So we have h represents the height of the surface, and which although this is not completely true for the full model, but I will discuss this about that, which will be considered as a relative height with respect to the average. Okay, so we have a diffusion term which is fourth order, and we have some instability which is there to explain the pattern formation in the deposit of the material. And then we have some nonlinear term which are responsible for the coarsening of these peaks and valleys that you see, which is related again to the physical phenomenon. At some point, the equation will just lose some of these terms. And so the first missing in action will be this one, which is from the physical point of view is an important term of the equation, but from the analytical point of view, in comparison with this term, this is, say, easy. I mean, this nonlinearity is much nastier. So this term will not get trouble. So we just drop it. Essentially, it's just easy from the analytical point of view because there's something which is much worse, and I will not get information on the local behavior of the surface, so we will not use it. And then there's also the linear instability, which I will keep it up to the point when I will discuss the convergence to the equilibrium, because the convergence to equilibrium is a little bit easier when this term is not here. You can manage to do the same with the linear instability. You just have to be a little bit more careful. And since the work was already quite complicated, we didn't consider this term. Okay. Finally, there is a driving force, which is a space-time white noise. And so which represents, I mean, in the model, some kind of fluctuation in the incoming particles. And the idea is, is already in the models that was proposed by physicists. Well, I mean, the idea is that you get really independence on what happens in different areas. And so the space-time white noise is the right model to consider. Here I've just listed a few references that consider this model in both in one dimension and in two dimension. Okay, so essentially the real physical case would be the two-dimensional case, because you would just deposit some material on a surface. So we are in 3 dimensions, so you're depositing something that you're going definitely depositing on some two-dimensional surface. But the one-dimensional case has also some meaning. For example, if you look at the section of this, you may recognize similar pattern, and then they would be modeled by the one-dimensional problem. The last remark is that this equation does not come from first principle. It's just, would say, like is some first-order approximation on some larger equation you would approximate by some expansion. So this. Let's say we are free to add or drop terms because there is no kind of first principle meaning of the term. So, okay, so let's start by killing this. From now on, this will be not here, and so we can consider a relative height profile. So we fix, this is the h is a value with respect to the average of it. So it will move, and so we will allow for positive or negative value of h, because otherwise, the point is that here we have a space-time white noise, so we cannot ensure that the solution will be positive. But while having a relative height, we don't run into this problem. Okay. Before going on, I will just before dropping the whole physics, I will just give an idea on how things work. Okay, let's imagine we start with the initial condition, which is almost 0, so there's nothing on the surface, and just consider large size. Here we shall consider periodic boundary condition, or lately we will consider the problem in a whole space. The idea is that if there are borders, they do not play an important role. Right, so we focus on the middle of the surface, and so we don't see the borders. That's why we can allow for periodic or no boundaries in the problem. So what happens? We start with a solution which is almost 0, and it is in a large set, and the first term which pops up is you see the other nonlinearity is not here, and I will switch to the one-dimensional case, which is going to be the main theme in the first part of the talk. So the linear instability gives some fluctuation with respect to the 0, and then all the nonlinearity starts creating some parabola-shaped hills. I point out that although the picture shows some kind of peak here, is not there. Here you may see could be some very small parabola. So, but it was very hard to picture this. So just allow me this. And in the end, we have the coarsening. So some large parabola kills a small parabolas, and so on. And that creates some patterns in the surface. Okay. Now we can start with the first part, which is the discussion on long-time behavior. And okay, how we shall do this? The problem is that we don't know how to prove uniqueness for this problem. And uniqueness here is mostly related, we are additive noise, right? So the uniqueness here is mostly related to the analytical problems of the equation, okay? Rather than on some local behavior of the noise, like in the previous talk by Carl Mueller. So it's simply, we don't know. And so what we are going to do here is to use a technique that we have done with Franco Flandoli. Actually, the main idea at the time was to use it for the Navier-Stokes equation. But it's general enough that can be adapted to different contexts. Here the problem is that we have a space-time white noise. So the technique had to be adapted a little bit. I mean, it didn't work straight away. And that's why we had to work a little bit also on this problem. Actually, the main interest when we started working on this was essentially trying to adapt the technique that we developed for the Navier-Stokes equation on this setting. So that's why we started being interested in the problem. Okay, so what's the problem? We don't have a unique solution. Okay, so we want to look for some interesting solution which has some additional properties. You don't know if, I mean, if the solution is unique, essentially you can get it is also a Markov process. I mean, they more or less go together. I mean, it's not a theorem, but in this setting would be close to. Okay, so the idea is let's try to see if we can get something out of some additional property. And the Markov property is quite reasonable because it's the one which is more, I mean, gives the dynamics, and we do believe that the dynamics should be the right object to study. Okay? And it happens exactly what I said. We are able to prove now that there is an invariant state and there is convergence to this unique invariant state. There are some subtleties in this statement because we may have different solutions. Each of these different solutions has a unique invariant measure and converge to this unique invariant measure. The problem is you may have a different invariant measure because you have different Markov processes. Actually, if all these invariant measures would be the same, the martingale problem would be well posed. So in our mind, we have that we have different Markov processes and we have different invariant measure. But at least if you consider one single Markov process, you know that this is extremely, I mean, it's a good Markov process. The behavior you would expect from the unique solution. You have a unique solution, you have a convergence to a unique invariant state because we have a space-time white noise. So this is quite reasonable. Okay? Okay, so now let me list the idea. The idea is the following. It's in two steps. In the first step, you try to show that there is a Markov process. In the second step, you show that this Markov process has some regularity properties. Okay, this technique is a kind of alternative to the technique that was introduced by D'Aprato and Debuche in their work. They base their idea essentially on the Kolmogorov operator. This idea is completely different. But in the end, it's, well, qualitatively gives some similar result. Okay, so what's the idea? The first step, you need to know that you can solve the equation. That's fine, fair enough. And then you can consider the set of whole solutions, right? For each initial condition, you consider a single set of all solutions that start from their initial condition. You may have plenty of them, you don't know, but then you can consider the set. Then you need to prove some nice properties of this set. For example, that this set is compact. Well, it's not empty, fine, it's compact. And the fact that it is compact is quite reasonable because as long as you can prove that you have a solution, what you essentially do, you essentially show that, for example, you have some kind of approximation to the equation. And then what you do, for example, by following Lyon's ideas, you just prove some compactness of this approximation. That's the compactness of the set of solutions. So that's fine.
So you use here that your noise is additive. So
in what I'm going to say, the fact that the noise is additive is but it's not a restriction. But here the noise is additive because it's what we are interested in. Is the model from the very beginning in those paper I showed before is additive. And then what you want to prove that you have a Markov process. So you try to understand if this family of sets satisfy a set analog of the Markov property. Okay? And once you do this, there is a kind of abstract machinery that was developed by Krylov that tells you, okay, there is a way to get one single element from each of these sets, put them together, and you get a Markov process. Okay? And that's the first part of the job. And then you continue and you try to get something more. And the technique to get something more is typical of parabolic problems. So in a parabolic problems in which you have some nice linear operator, you know that you have some existence of weak solution, but you know that for a short time you have a strong solution. I use weak and strong as in PDE sense. So I will be quite careful. Whenever I say weak and strong, it means in PDE sense. I will use weak, the parabolic, probabilistic weak, I will say martingale solution, so, right? So I just say now, just to make it clear. And the fact that, so this kind of uniqueness is, the non-uniqueness problem of this kind of equation is not clear. I mean, we will discuss this later. But the advantage here is that you have a parabolic problem with a good linear operator, which is essentially a fourth order operator here, so it's very regularizing. So what you get is that for a short time the solutions are all the same, and you will exploit this. And then with this we have regularity properties of the transition semigroup, which means a strong Feller, and then we have some easy irreducibility property, and we get convergence to the invariant measure. Okay, let's see in more details how it works. Any question? Because now I'm going to show all this, but that's the scheme of the whole proof.
Yeah, this short time coupling with the smoothest problem. I mean, you can, I mean, in the beginning I understand this, but I mean, you have a long time kind of some estimate in the long time for the.
No, that's the point. We don't have any good estimate in the long time, but those that come from the a priori estimate for the weak solution, and that's why we need the Markov property. With the Markov property, we can reduce a problem in long time in a problem for short time. The idea is that what we are going to prove is this strong Feller property, which and strong Feller property is a good one, because if you know that it happens in some time, then it propagates. Okay, so that's the main point. I mean, that's the trick works because you have both. Okay. Okay, let me discuss a little bit of the Markov property, and just to give some definitions. First, I need to define the path space. I will see later what is E, and which is going to be the state space for the problem. Actually, it's not really important, but we will see. And then we define the canonical process, and what is a Markov family. And this Markov family is a family of probability measure that satisfies the Markov property. I wrote this in terms of the Markov kernels. You may write it the way you like, but that's it. And the Markov kernel is essentially the probability that the process hits some set A. Okay, so that's the idea. You have an initial condition, and you have the evolution, and you want to hit A, which one probability. And then you can decompose this probability in terms of some intermediate time. You just integrate over all passage places of the intermediate time. And that's it. So what's the idea? Now let me explain in a way that it would be useful for the next slide. You have some probability measure that gives the probability of each path from time from 0 to S, right? And then conditional to S, then you continue with some probability which is given by an element of the same family, but starting from a different point. Okay? So now, what is a set analog of this property? Well, simply we have to allow not for exactly the same quantity, but from a quantity which belong to the same set. Okay? So it's if this is the this is Y. I will do with the figure. If this is Y, right? So this is a path which has been chosen with the probability measure which correspond to Y. But if we have more than one, we just allow for any of this. Okay? So what is the set value version? Now we consider a set of solutions, because we don't know if there is one, there can be many. And then we have to think of this x as the initial condition. So that means that all these probability measure will give mass 1 at time 0 to the initial condition. Okay, so the two properties I need are the disintegration and reconstruction. In disintegration, you simply condition with respect to time s, and you want the dissolution to be a solution starting from where the solution is at time s. Okay, here there should be some translation in time, but just to make it simple, I didn't do that. The problem is, time homogeneous, so this is not an issue. And then we need another property, because the Markov property, in a way, is both. You get from right to the left is reconstruction, and from left to right is disintegration, right? From left to right, I get one probability measure, and I write it as a superposition of probability measures. And then it's from right to left is the other way around. I have a superposition of probability measure, and I identify all this superposition as a single probability measure of the same class. Okay? That's exactly the same, but we allow for the whole class to be part of this game, right? So, for example, the reconstruction, so for the superposition of solution, I have a family of probability measures which belong to the right spaces. If I make a superposition of this has to be a solution starting at x. Okay? So that's essentially the idea. Okay, so now how to select an element from each set so to have this property to be stable, because we have the set of all solutions, and we know that this is true, because if we make a disintegration with respect to the solution of a stochastic equation, all this set-valued Markov property is going to be true. The problem is how to select one single element. So the idea is to shrink this set and to make it more and more small. Smaller and smaller. So in the end, you can get only one element from each set. So how to make it? The idea is since we want to do it in a measurable way, because this measurability is ground level. Otherwise we cannot integrate. We want to get some measurable selection, so-called, which also is keeps a Markov property. Okay, so the idea of Krylov is a paper of 1973. What it does, he finds a family of functions that are maximized. So you start from a set C of x, you consider the maxima of these functions, and then you iterate. And these functions are essentially the resolvent. If you would have only one solution, it would be essentially the resolvent of the transition semigroup, right? And the resolvent are very nice because, in principle, you have the resolvent formula, and so this is exactly the kind of function that keep the Markov property. Okay? So what you can prove is that you consider this set, you make it smaller by consider only the maxima. And since the function is made in this way, you can prove that all the two properties of disintegration, reconstruction are stable. So you get a new set which is smaller and which keeps the same properties. And then you keep repeating, because here you have some freedoms, you have some degree of freedom of lambda, degree of freedom of f. I didn't say what they are, but you can choose many of them. And if you can choose an infinite number of them, then you end up with something, you just do it, you start with the first, second, and so on. You get a smaller and smaller set. And in the end, you end up with only one element. So it's obvious that if you start with, even if you change the order of maximization, you may get a different element, okay? So this doesn't say that there is only one Markov process. It just says that there is a Markov process. Actually, if one can prove that there is only one Markov selection, this amounts to prove that the martingale problem is well posed. So, we keep in mind that we may have several Markov processes. Okay, so this is the theorem. How difficult is to adapt it to the infinite dimensional setting? Well, there are two main problems. One is pretty clear. The other one is, I will explain it when we will come to the issue. The first one, the obvious one, is the problem of topologies. In finite dimension, you have Rn, and okay, you may put some weird topologies, but you don't do that. I mean, in infinite dimension, it's natural to have different topologies in the state space. You may have, because the solution is continuous in some topology and maybe is just summable in some stronger topology. So you have to keep into account that, for example, you can solve the problem only with some initial conditions, but you get compactness of solution in a larger space. Because that's how things go in this PDE stuff. Okay, so one of the main point to adapt this method is to keep into account the topologies. We shall see that the state space essentially play no role. You just try to take the largest one you can, as long as you get compactness. So, initial condition is a differential. And then there is another problem, which is typical of this kind of PDE I'm talking about, and that I cheated. I talked about Markov processes, Markov solution. This is not true. We will see that these are not really Markov processes, and sometimes are not allowed. And those times might be the time where the solution has some loss of regularity, and so you lose control of the problem. And in order to restore the full Markov property, we need some additional regularity. That's what we shall prove in this strong failure part. So in the end, we will get a Markov process in a smaller state space. Okay. So in this setting, the main problem is to define what is a solution. Because, I mean, the whole Markov selection theorem works as long as you ensure that the set of solution has the properties of reconstruction and disintegration. So the main issue is to define the solution in such a way that you get compactness of each of these sets, and you get the two nice properties, Markov set properties, right? So the main issue in this, for using this technique, is to understand what is a solution. Okay, let's start to the standard one. Let's say weak martingale solution. I remember weak means PDE weak. Martingale solution means probabilistic weak. Okay, so this is some standard regularity requirement. We take as initial condition the space L2 or some finite domain. And I will not specify the state space because we just need a large state space to ensure compactness. If just, I don't know, some much larger space than L2. It doesn't matter which one is. This is just a technical requirement. This is necessary because we can solve the equation in L2. Okay, okay, all the properties are standard. Let's keep to the other. Let's focus on the last one, because the last one says that this is a weak solution to the equation. But it says this in is a stochastic equation. So what we do, and it's also PDE, we test the equation against a test function which has to be smooth and so on. And we want these to be exactly equal to the forcing tested against the test function. And we say it in a different way. We don't say this is the Brownian motion, some linear process tested against the test function. Because we consider weak solution in probabilistic sense. So we do not have a linear process. So what we say is that this probability measure is a weak martingale solution if this process is a standard Brownian, well, is a Brownian motion with diffusion coefficient given by L2 norm of the test function, which is what you would expect if you have a space-time white noise, because that's exactly, if you test a cylindrical linear process against the test function, that's exactly the variance you would get. It's a Gaussian random variable, real Gaussian random variable with this diffusion coefficient. So I'm just rephrasing what is. Okay, if we consider this solution, we don't go too far, because one of the issues is to show that solutions are compact, and this solution has not enough regularity to ensure compactness. We need to do it better. The problem is that here we are dealing with space-time white noise, so we cannot use some Ito formula and so on. We have to do things a little bit more carefully. So let's see how. The idea is the following. First, we construct the linear process. What we do, we choose as a test function an element on an orthonormal basis we have a periodic boundary condition of some set 0L, so you may just use the Fourier basis. That's fine. So it's infinity, it's fine as a test function, and so we consider that martingale with respect to the element of the orthonormal basis. Since this is an orthonormal basis, it turns out that all these processes are independent Brownian motions. Okay? Because I mean, you just do the computation, and so you can write down what is the Wiener process. And once you do this, you can even write down the solution to the associated Austen-Uhlenbeck process, right? Say starting at 0. We are going to change this, but say starting at 0. And you can do this all pathwise, and you ensure that you have a continuity, because the state space, okay, it's not written here, but it's a space of continuous functions. Okay, so you end up with a process which has something which is continuous, which is a solution of this problem. Okay, so here you see that is really a weak martingale solution, because we have a solution and we construct the associated Wiener process. So essentially, the Wiener process is a function of the solution, right? So it's definitely a martingale solution. Okay, now we have all these, and we need some a priori estimate that we want to use in the PDE. So we write the a priori estimates in terms of some of the solution. So which kind of a priori estimate we have? We have essentially two a priori estimates. The first one is this, and we are going to use this. There is another one, which, to be honest, we didn't find a way to use it. although I mean, the story is not over. We will see at the end. And okay, so now I focus on these a priori estimate. I will write it in a different way, and the different way is the following. So I consider a special class of solutions, we call them as energy solution. Why? Because they satisfy an energy inequality. Okay, so energy solution is a martingale solution with some additional regularity. Some additional regularity, it doesn't matter, just technical. Let's go to the meat. This solution satisfies an inequality with probability 1. Okay, we have V and Z. Z is the Austen-Uhlenbeck, and V is the difference between the solution, well, actually it's the canonical process, but on the path space, I have the law of the weak martingale solution. So the canonical process is under the law, under the weak martingale solution, is the solution. So this is the solution, and I minus the Austen-Uhlenbeck. So in this way, the V satisfies a PDE with random coefficients. So I can do some estimate without using the Ito formula, Ito calculus. Okay, that's the main point. And the kind of computation we do is essentially doing this estimate on this energy, which is the a priori estimate I show you, but with some manipulation, because you need to. Okay, the problem is that we consider the set of all solutions, right? So we cannot do any computation on this, because most of the computation you would like to do, you cannot, because you don't have enough regularity on the process. So the idea of adding to a solution the properties that the solution needs, is due to the fact that we cannot prove these properties in any other way. So we have to incorporate these properties in the solution, because we don't know, when we are going to do all the selection procedure, we don't know which kind of solution we are going to pick. For example, we show that there is existence of a solution, at least one solution, by some method. You have plenty of methods at your disposal, but then we pick some solution. We don't know if the solution we are picking is the one we got by some approximation method, right? So we cannot prove anything on that solution, because essentially, although we cannot use Ito calculus, but we cannot even use the standard calculus, because, for example, this thing is not differentiable in time. So you can prove it that there are solutions with this property, but you cannot prove it directly on the solution, right? And that's the problem, because this thing is not differentiable in time, is not even continuous in time, and so you cannot ensure that this inequality holds for all time. There are some times in which this doesn't hold. Fortunately, this set of times is small. Actually, it's a measure 0 with respect to the Lebesgue measure on the real line.
What is new in your E nu Z? I mean, down in your last expression, what is new?
This one. Oh, this is a definition. V and this is a function of V and Z, and this is, and here is evaluated in capital V and capital Z.
Okay, I'm sorry.
This is just a definition. Okay? Okay. Okay, there are a couple of things to say of the energy. The first is the energy inequality is stated as a probability 1 for all S which do not belong to this set of, this is the bad times, but probably the solution is losing regularity. But, I mean, I don't know if you notice it, this set is a deterministic set in a way, is an almost sure set. I mean, it does not depend on the path. Actually, this is equivalent. You can either consider all these times to be path dependent, but this is equivalent to have a single set which is not path dependent, which is in a way is counterintuitive, because I would associate this time to the times in which the solution may lose some regularity that might be path dependent. So I mean, my interpretation is that essentially the stochastic forcing we use here is, I mean, this set is in a way stable with respect to perturbation. So it comes from a more peculiar part of the equation, does not come from the driving force. Okay, that means it's stable with respect to the driving force, so that we can get path dependent or not path dependent, and this is because this is a peculiar property of the equation, not for the driving force. Okay, then here, okay, I thought I could be taking less time, so let me skip this. Actually, here we need not only the Ornstein-Uhlenbeck, because in order to control the convergence to the invariant measure, we need a little bit of contraction. And so that's the way we add contraction to the problem. Okay, let me skip this, but the idea is that in order to show that there is convergence to the invariant measure, we need a little bit more contraction. And that's the way we do it. I mean, it's classical. I mean, this is a standard. Okay, and so, okay, let's give the first theorem. The first theorem says we have a Markov family. Okay, there are some times in which things do not work, but it doesn't matter, because most of the time it will work, and we will see that for all time it will work if we consider a smaller state space, right? So we know that there is a Markov process, which is a solution of the equations. Fine. So the first part of the strategy is complete. We have a Markov process. Okay, let's go ahead and let's try to understand this short-time coupling. What it means? Well, essentially, it means that if you start from a regular initial condition, this is kind of PD theory, for a short time, you have a smooth solution. And then you may have a loss of regularity. You don't know. If you don't have loss of regularity, then the solution is smooth, is unique, and so on. But you don't know, and so you may only give estimates on this time. So what is the idea? The idea is that starting from any initial condition which is smooth, and that's why we need to consider a smaller state space. So initial condition should be smoother. We can solve a weak solution for any initial condition L2. To get smoothness, we need to consider a smaller set of initial conditions. So in this case, we consider H1, but you can make it better. Actually, we know that you can go up to H1/2, but I mean, this is technical. Okay? So for each initial condition, you start and the solution is unique. And then something might happen, and then you may have many different solutions. But at least for a short time, there is only one solution. And so you can couple any solution to one single process, which actually exists up to some time. Okay, this the technicality. I mean, there is some technicality involved, but let's state in this way. I mean, I should be more precise, but let me be less precise, but hopefully more clear. Okay.
This is the amorphous part.
So you start from initial condition x, and this x is regular, and so you know that for a short time, tau tilde, there is a process which agree with the solution up to that time. Okay, I wrote this in this way, but the idea is that if you fix some t, and you know that this kind of departing time, which should be this one or this one for another instance, and as long as t is smaller than this departing time, the two processes agree in distribution. Actually, you can do even better, but for our purposes, in distribution is fine. Okay? So in this way, you can control any solution. You don't know which one you have picked by the Markov selection, but it doesn't matter because you know that at least for a short time, any of these solution will agree with this regular one. Okay? Because it's a local uniqueness. Now this means we can do some computation of the solution finally. So the kind of computation that we do is we try to approximate the transition semigroup. And if you do this, you can control the difference between the two semigroups with the probability that the parting time is smaller than t. Because as long as the parting time is smaller than t, you lose control of the problem. So you just control this probability with this. Okay, there is a norm of phi missing. Assume that the norm of phi, the supremum, is smaller or equal than 1. And then this is true. Then you have these two probability, but actually these two probability are the same. Because the probability that these two probability are the same because these two agree up to time tau. And so these two probability are the same. And so actually you can estimate this difference only through this term. So you have full control on this departing time because it does not depend on any of the Markov solutions. Okay? And that's it. Oh, here is something mixing. Because then if you want to show smoothness of the transition semigroup, what you have to do, you have to control two terms. The first one is the difference between this semigroup and the smooth semigroup. And that's it. It gives by this, and you have some exponentially small control on this element. And the second one, you have to ensure that this smooth semigroup is smooth. I mean, I use smooth in meaning that it refers to the smooth solution, but actually is smooth. I mean, you can prove that this semigroup, with the assumption we have that is space-time white noise, this is smooth. It has the Stromfelder property. That means that pt phi is continuous. P tilde t phi is continuous. So you have two terms here. One comes from the continuity of the smooth semigroup, and one comes from the error that you make by replacing pt with p tilde t, right? And okay, what you do? Oh, this is something missing. Okay, then you balance the error. Okay, actually, unfortunately, there is one thing missing. Let me write it on the blackboard. The one thing missing is there is one thing missing, and so I will take the occasion to answer to your question, and is how can we manage to do this at any time? Well, the idea is simply that if you have a semigroup, and being this a semigroup is part of getting the Markov property, because you can read the Markov property in terms of the transition semigroup to be a semigroup. So what you do is simply you do this. Okay? And now you forget about this, because now I'm going to bound this with any bounded function. And this is a contracted semigroup, so this, if phi is smaller or equal than 1, then pt minus epsilon phi is also minus or equal than 1. So this gives uniform estimating time with respect to t. Okay? And so the problem can be reduced on the smooth semigroup and on a short time. And that's good because I'm going to choose epsilon. Now I have a 1 degree of freedom, which is epsilon, and I choose epsilon so that it matches this. And so in the end, I have a modulus of continuity of this thing, which is just given by this. And so I can get a uniform modulus of continuity with respect to t. Well, okay, this is not completely true because here there is it cannot be completely independent of t, because from t equals 0 it has to degenerate, because for t equals 0 you don't have continuity. But anyway, up to the fact that t has to be larger than 0, you get a control of this. Okay, and then what you get is that this solution are have the Stromfeller property in H1, and actually they make a Markov semigroup, they make a Markov process in H1. So there are no exceptional time. When the initial condition is in H1, then there are no exceptional time. Let me stress that this does not mean that there is regularity of the underlying PDE. This is not true. You just don't have this exceptional time. Okay, then you get a full Markov process on H1, which actually gives a semigroup which is Stromfeller, which is good because now we are going to try to understand if there are invariant measures and if there is convergence to the invariant measure. And this semigroup, at the level of the Markov selection theorem, they are not even Feller. So it's a little bit trouble, I mean, to show the existence of invariant measure, and by the fact that we have Stromfeller, we get the invariant measure back. So let's see, the theorem in this setting is actually we have consider a family of martingale solution, and then there is a unique invariant measure. Okay?
It depends on the measure, depends on the selection.
Exactly. So how you do this? Well, actually, it's in a way kind of funny because uniqueness now is easy. The issue is existence. Because uniqueness, we have a Stromfeller property, and there is a control argument that gives irreducibility, and then as long as you have an invariant measure, this is going to be unique. Now, so we have to show that there is an invariant measure. So we need to have some estimate, and we do this with the energy inequality. That's why we need the energy inequality, and we need a little bit of contraction, and that's why we needed some modification of the Orstein-Uhlenbeck operator. But then we choose the right contraction, we use the ergodic theorem, and we get the proof. Okay. Let me discuss. Okay, that was the first part. Sorry, I was too.
What about the set of solutions for convex and compact?
Convex is a technical requirement. Compact is.
How do you get convexity?
They are probability measures. So they are solution to the equation. So any property is either probability one property or it's a combination. So you get it. Okay. Now, still, okay, what we had is we have a Markov process. It converges to a unique invariant measure, but still the main issue is open. Do we have a unique solution? In which sense we have it? In probabilistic sense, PDE sense, we don't know either. Okay, to be honest, the minimal chance would be to have a solution which is unique in law, which actually would be even the most interesting part, because when you do experiments on this problem, the only thing you get are statistical quantities. So as long as the statistical quantities are the same, you don't even really need to have a unique solution pathwise. You really want to know that the statistics you are getting are really the good one. But to be honest, we do not have a way to prove uniqueness in law. No. So let's try to understand if there might be some blow up at the level of the PDE, because I mean, this would definitely give some information. Although, I mean, again, I stress that uniqueness and regularity are different topics. And this also is meaningful with respect to the stochastic equation. And that's now what I want to discuss. Why? Well, because you may have a smooth PDE, which has a very nice properties, but if you add a noise, then you are going to kill most of these properties. Because if you have a space-time-wide noise, you cannot hope to have any better regularity than the one that comes from the driving force, but which is a general principle. Is input-output. If you make an input a rough forcing, you're not going to get regular solutions. So now the question is if there is any blow-up, at which level we get this blow-up? Do we have it at the level of regularity of the noise or not? Because we have to understand if the PDE has a blow-up, and so has a loss of regularity, but this loss of regularity does not influence the regularity of which the solution of the stochastic equation lives, then this is not going to mean anything for us. On the other hand, if the loss of regularity happens at the level in which the stochastic equation is still meaningful, then this would be meaningful. Okay, what I'm going to say is not a theorem, but just my belief, and is related to blow up for PDE with noise. Okay, because you may try, the problem is that you may show that the PDE is regular, or you may show that the PDE has a blow up, but these may not mean anything for the stochastic equation. The idea, I mean, say the problem has a loss of regularity. So the loss of regularity has to be at the level of regularity which is seen by the noise. See, okay. And then it has to be in a way stable, because you may have a very peculiar geometric condition that leads to the blow up, and the generic property is not to have blow up. And so it's maybe reasonable that if you add a noise, you don't see this area. On the other hand, if blow up is fat, then the noise is not going to destroy this. And if you have a fat blow up, then even the stochastic equation will have a loss of regularity. I mean, this is you already saw this. I mean, this idea in the talk by Franco, which was discussing all the thinness and fatness of the set of uniqueness, and so on. The idea is the same. I mean, as long as it's thin, adding a noise may help. But if it's a fat, then the noise, essentially additive noise, does not destroy the structure. Okay. So now we want to understand if the noise may destroy the structure or not. And the answer will be, unfortunately, no. Because we have some criteria for blow up that are compatible with the structure of the noise. Okay, before going on, I want just to give some pros and cons on this blow up. Well, the coarsening phenomena that we saw at the very beginning may suggest blow up, because this area would be the most candidate for loss of regularity. And indeed, by the estimate we have, the blow up in the loss of regularity in negative part of the solution is more likely than the positive part. Okay, so, and this comes in, I mean, and here is the second a priori estimate we would not know how to use. Essentially, we get this by this a priori estimate. Actually, there is a paper by Dirk and his collaborators in which they have they compute some numerical approximation, and what they observe is that the approximation rate is essentially strongly stable with respect to the level of approximation, which might suggest that the solution should be regular. So it's not clear. And then we try to understand if for the deterministic equation there are some stationary solutions. This is one, and this has a singularity, is a logarithm. And this is periodic, so perfect. And this would suggest that this is not really a solution, because, I mean, if you do the formal computation, you get 0, but actually here there is a pole, and so you may see something really appears at the level of distribution. But anyway, and we were not able to find a self-similar solution to the problem. Although any computation we tried so that the self-similar solution would not be global. That's what you need for a self-similar solution. So really, we don't know. I mean, there's some people here that knows very well PDE, so they might get some ideas, but we didn't. Okay, so we got some blow-up criteria, and these blow-up criteria are essentially compatible with the noise, because all these regularity would be okay for some, at least for the linear part of the problem. Then the nonlinearity may add up some other phenomena, we don't know, but for the linear part, all these things are quite compatible with the noise. So this suggests that if the deterministic equation has some loss of regularity, has some loss of uniqueness, this is likely to be true also for the stochastic equation. I stress again, we are not in the case of Carl Muller's talk, in which there is a multiplicative noise, and so the noise is playing a much more important role. So here is additive noise. So, and this suggests that the deterministic part is, in a way, is governing the phenomenon. Okay, now let's see that there is blow up actually. Now this is just a small computation, and is a cheating, because okay, we in a way we were inspired by a work by Lee and Sinai on the Navier-Stokes equation. And what's the idea? Okay, the idea is the following. Let's write the equation in terms of the Fourier component. We are a periodic boundary condition, so we can do this. And if we consider the real solution, then there is a relationship between the different components, right? But now let's make a simplification. We consider this subset in which all modes with the negative frequency are 0, and all modes with positive frequency are positive. This is a closed class for the dynamics. You can show that there is a unique solution in this class. And why? Well, simply because if you consider this class, the equation is reduced to this one. So each mode k only interact with the previous mode.
What is this equation?
Oh, this is the same equation, but in Fourier component. Okay? So, oh, no. No, here is much simpler. It's much simpler. So what you get this, right? So you get a much simpler problem in which the mode k interact only with modes smaller than k. Okay? This problem has a unique solution because you can stop any k, and this is an equation in Rk, and then it has a unique solution. Then you prove that okay, so the solution is unique, and you can prove. Now they are just pictures, but believe me, you can prove it. And this is something we are doing. We did actually. We haven't published it, but we already did all the computation, and there is something in one of our paper. What happens? Each of these components, you can prove that converges to 0 at infinity. So that it has a global solution. Each of these components, the solution is global, is unique, and each of the component goes to 0 at time infinity. But still, there is an accumulation, a concentration of mass, and you get a loss of regularity in some when you measure with respect to some, say, infinite dimensional norm. So how it works? Okay, now, again, I ask you to believe me. This is the picture of all modes. Each of these modes has a maximum, and this maximum is traveling in time. Okay? So the first component has a maximum here, the second component has a maximum here, and so on and so on. But there is an accumulation but this speed of the maximum is very small, so that in a finite time, you get a maxima for all components, right? And so when you sum up these, you get something which is infinite. But each of these is a smooth function, very nice, goes to 0. The blow up is given by the accumulation of maxima. Okay? So it's an infinite dimensional phenomenon. For infinite dimension, it does not happen. Infinite dimension, all this problem is nice and has a unique smooth solution. But the accumulation of energy here around the limit of maxima gives the blow up. Okay? What this says for the original equation? It simply says that if you are going to prove anything about the equation, it's not going to work with the energy methods. Just estimate. It will not work. Because whatever you can do on the original equation, it should work also in this case. And in this case, everything goes wrong. Okay, that was just nice. And then you see if you add modes, this is only for the first 10 modes, 15, 20, and then you see it's going up and up. But then it's going down, you see? And the larger it is at the beginning, the faster it's going down. Okay. I have, let me check the other. I have 1 minute. I have 1 minute. And let me discuss about the two-dimensional case, which would be the physical one. Okay. We have just actually, let me say, is the first preprint of the program here in Newton Institute. We just made a work on the mild solution for the two-dimensional case, following a suggestion of Herbert Koch, which he developed a method to get a mild solution essentially he suggested to follow his idea that he developed with Tataru in his paper in 2001 on Navier-Stokes, and which actually what we did. And so we have some results on mild solution, both in deterministic and stochastic case, although we cannot still get the space-time white noise. That's why the partially means we can solve the stochastic equation, but we have to allow for some little bit of smoothness on the noise. Space-time white noise is not obvious, because in 2 dimensions it's not even obvious how to understand the space-time white noise. So we're working on these. There are some ideas. Some of these, for example, suggested by a paper of Da Prato with Debuche. We're trying to do this. So the partially means some is done, something should be done. And then there is the issue of weak solution. We would try to get the same results for the two-dimensional case, and we were out of hope until there was a preprint of Michael Winkler, which he, using this quantity, he managed to get some weak solution deterministic case. And now we are working with him to extend the results to dimension 2. And I have some other 4 slides, but I think that's enough for today. Thank you very much.
Does the blow up happen at isolated points, or is it on?
I don't know. I have no idea. Unfortunately, I mean, did I know this? I would essentially know how to manage the problem. Yeah, but I mean, an isolated point would just. I mean, my intuition would just say that you don't get a blow up in the stochastic equation. That's my understanding. To get a blow up in the stochastic equation, you have to have a fat blow up, which usually happens. So.
Is it when you had your initial setup, you had a point to start with, and then you had a cone or compact set?
Yeah.
Can you raise the problem to a Markov process on the compact convex, and then use a Hausdorff topology? Would you get a Markov group on that?
No, sorry, I don't understand. I mean, the compact convex are the sets.
You might just think of a bunch of them evolving, so you get compact sets.
Well, actually,
This would be your point.
okay, let me say the Hausdorff distance plays a role because we need to all these maps, set value map to be measurable, and so you actually get measurability with respect to the Hausdorff. I mean, the topology given by the Hausdorff distance. Okay, the Borel sigma are given by the topology of the Hausdorff distance. So it does play some role. I'm not sure I did understand what you mean.
But if you have a Markov process on that space, then you can ask.
Oh, compactness is a compactness of the probability measures. It's not compactness of the flow given by the Markov process. So no, that is not compact at all. I mean, it's, but I mean, maybe now I understand your point. Oh, you want to lift the.
Yeah, and then you get an invariant measure which you can compare with the selection you want to get.
Yeah, actually, this was already suggested.
Crazy idea.
I think it does not work. I mean, it's.
Any other questions? Okay, so let's thank everybody again.